Yeah, thank you, everybody. It's great to be here. I've been, looking forward to giving one of these talks ever since I moved here about a year ago. I got my PhD at the University of Arizona, and now I am a postdoc here. And I wanted to tell you a little bit about going to weird places to do astronomy. And so that's actually where I learned how to solder. And as proof, I have this glorious picture of my behind, taken from a webcam looking into the cabin of one of these telescopes right down here. Normally they're just there to make sure that everything looks fine and isn't broken. And at this point, we have this beautiful, beautiful footage of me. So this evening, I want to kind of talk a little bit about, going to these strange places to do kind of cool astronomy. And so there's two big facilities that I want to focus on. The first one is this, too far, telescope called the South Pole Telescope. I bet you cannot guess where this is located. And so this is actually, as the name suggests, it's located at the South Pole. And this was originally built and designed specifically to look at the cosmic microwave background. So this is all the light that's left over from the Big Bang. It's been heading in our direction towards Earth ever since the universe was created. And now finally, just at the present day, that light is hitting our telescope, and we're there to pick it up from the South Pole. The other cool one that I want to talk about is this telescope called ALMA, which Sam also just mentioned. So this is the telescope that's at 17,000 feet. It's on a big, dry plateau in the Atacama Desert in Chile. And so you might have noticed that this looks like one basically large satellite dish, like TV satellite dish. And this one looks like a whole collection of a bunch of them. And actually, I couldn't even find a picture that had everything in there, because you can only stick those antennas so close together before they start running into each other, and nobody likes that, as it turns out. Especially not the people who built them. So the first question you might ask is like, well, why do you need to go to the South Pole to do astronomy? Like, that seems kind of weird. And so the first thing that a lot of people say is like, oh, well, from the South Pole, it's dark for half the year at a time. So once the sun goes down, it's down and out, and that's it. But that's actually not why we built this South Pole telescope at the South Pole. The actual reason is because of aliens. No, that's actually also false. So for a long time, there was this great conspiracy theory that I loved, that NASA discovered Nibiru, this planet X, and it was going to hit the Earth in 2012. I'm sure you all remember this. Like, we were there. It was the apocalypse. Only the people in this room survived. And so we got these crazy YouTube videos. People like, I cannot tell you who I am or how I was able to obtain these photos. And it's like, some random red blob. Like, give me a break. And so we like to make fun of this a lot, which also inspired my T-shirt. We have these greetings from Nibiru, the aliens. This is exactly what we're finding. Okay, so no, this is actually also not why we would build a telescope at the South Pole or at this crazy desert in Chile. The actual reason has to do with the stuff that we're breathing right now. So air is kind of a problem for some parts of astronomy. And so what's shown here is basically, if we go up here to certain wavelengths of light, air is transparent and it lets light through. So like the light that your eyes are seeing and my eyes are seeing right now, that light can travel through air and come, basically without any effects. But there are other kinds of light that can't do that quite so easily. So like UV light is not very good at getting through air. So this is good for us because if we get too much UV light, obviously we get cancer, and so that's bad for living things. Radio waves travel through the air very, very easily. So that's why we have AM and FM radio. That kind of light is very easy to pass through air. The kind of light that we care about if we're going to look at the cosmic microwave background or some of the galaxies that I'm going to talk about in a bit is kind of just a little bit up in energy from radio waves, but not quite all the way to like the infrared that Casey or Matt were talking about. And so we're kind of sitting here in these little chunks right here. Oops, sorry about that. Yes, Nibiru. So we're trying to sit here in Nibiru, where the air is kind of like a little bit of a problem, but maybe we can make it be less of a problem. And the big thing that hurts us for observing this kind of light is that there's water in the air. So this is another thing that's good for you and me, but bad for astronomy. And so just as sort of a demonstration, here's what that transmission looks like from central Texas. So up here at the top, the air would be completely transparent to this kind of light that we want to look at. And down here, it's completely opaque. So the light can't make it from space down to us. So this is central Texas. And actually, this isn't even central Texas because I couldn't find any calculator that would give me this curve without crashing for the amount of water that we have in the air here. You might have noticed it's been a little humid lately. And so this is what that looks like from the South Pole. So now you can see that in general, we're looking a lot better. See, there's still all these like deep notches and stuff where the light still can't make it down from space. And that's mostly due to things like ozone and molecular oxygen, the stuff that we also like to have in our air. And so just for reference, the thing that we use to sort of talk about this is called the precipitable water vapor. And all that basically means is like if you could take all of the air or all of the water out of the air directly above you and sort of condense it down into a liquid, how much water would there be? So over the South Pole, there's like about 0.5 millimeter of water between you and space, and that's it, if you could pull all the water out of the air. In central Texas, we're talking more about like several inches of water. So that is kind of a problem for this, and that's why you wouldn't build a telescope like this in San Antonio. That would be a problem. Okay, so the South Pole Telescope, we just celebrated its 10-year anniversary. It was completed in late 2017. And so since then, it's been making these big, beautiful maps of the cosmic microwave background. And so just for reference, this is the full moon to scale. And here's what that giant map looks like. So all these like little wavy fluctuations, all these blobs, that's actually real. That's not noise. That's not garbage. That's actually the imprint of the birth of the universe. And so that's pretty cool. So just for reference, this is 2,500 square degrees of sky. And if you hold your fist out at arm's length, that's about 100. So this is like 3 fists by 8 fists or so. So it's a pretty hefty chunk of the sky, but by no means close to the whole thing. So I just want to kind of zoom in and see this. So this telescope is observing all this light that comes to us from the birth of the universe. But of course, there's like other stuff in the universe between now and then. So here's just kind of zooming in on that map. And so the resolution that this telescope can give you is no better than your human eye, actually. So the resolution of this map is the same as your eye can give you. It's just that the wavelength that this telescope is looking at is hundreds of times longer than your eyes can see. And so you need a really big telescope to get even, okay resolution. And so if I zoom in on this, you still see all these wavy, blobby patches. And so that's still that cosmic microwave background light coming to us. But you also see there's all these like bright blops and dark holes and things. And those are basically coming from different objects in the universe that are between us and looking at the Big Bang. So all of those like dark holes in this sky, this is coming from giant clusters of galaxies. And so the key thing about clusters of galaxies is that they have a lot of really, really hot gas in them, like 100 million degree gas in them. And when one of those cosmic microwave background photons hits that very hot gas, it gets bumped up to a higher energy. And so then it's not really the same wavelength as the cosmic microwave background anymore. And so it shows up as a hole. It's basically a shadow that this galaxy cluster is casting on the CMB. Some of these other ones are galaxies actually a lot like Matt talked about. So most of these bright spots are galaxies, quasars, with their jets pointed directly at us. So these are exactly the kind of blazars that Matt was talking about. And so here's just kind of an image of one of them. This is not pointed directly at us. You can sort of see really faintly here this jet, and then it's blowing these huge lobes of hot gas. And so basically most of these bright spots are if those jets were pointed directly at us instead. But this picture is a lot prettier, so I like it better. A very, very tiny number of these bright spots are actually baby galaxy clusters. So like Casey said, when you look at this picture of a galaxy cluster, all of this is orange and red light. And so that's telling you that this is all old stars that have been living for a very long time. But we're actually also able to see a very tiny number of galaxies that are still forming. And the way that we know that these are forming, these ones are orange not because they're old, but because they have a lot of dust in them, which I'll talk about in a second. And so this particular case has about 15 galaxies that are about the same size as our own Milky Way galaxy, and they're all within about the distance that you would take to get to Andromeda, which is the closest big galaxy. You can see it with your own eyes. So if you lived in one of these little baby galaxy clusters, the sky would probably look a lot more interesting than our current one does, because there's just so many cool galaxies right by them. And then the last sort of big chunk of what these bright patches are these galaxies that I like a lot because they're really cool. These are very distant starburst galaxies. And not only that, but they're what we call gravitationally lensed, which I'll come back to in a second. So basically, if we then go take a better telescope like ALMA and zoom in on this, what we a lot of times see is this ring of red stuff. And so this is actually the galaxy that we originally saw in this SPT map. And the reason that we're able to see it at all in this map is because it's directly, almost exactly perfectly aligned behind another galaxy from us. And that foreground galaxy bends the light from the galaxy behind it around that foreground galaxy, and we come up with this nice, pretty ring structure. Okay, so I mentioned dust, so I want to show you what an astronomer means by dust. This is not like household dust crap, which is like mostly your skin cells, which is even grosser to think about. An astronomer's dust is also not very fun. It's more like smog or soot or even like a very fine sand. This is all stuff that we call dust. And the thing that this dust does is that it blocks the kind of light that your eyes can see. And it really, really blocks ultraviolet light. And so if you have some of those young stars that were just born that Casey was talking about, and you stick a little bit of dust in front of them, that light from those young stars can't get to us anymore because the dust blocks it. And so here's an example of a galaxy where that's happening. This is a galaxy called ARP 220. It's the closest of these really dusty galaxies. And so this galaxy is pretty nearby, and it's forming stars about 100 suns worth every year. So that's about 100 times faster than the Milky Way is. And yet if you look at this image, there's not a whole heck of a lot of young blue light there. There's not really that pinkish glow that we were seeing in Casey's images either. Instead, what we're seeing is all this really dark, blobby, patchy stuff. And this is the dust. So the place where all these stars are forming is sort of right down here in the middle, but it's behind all of this dust. And so we can't see it anymore. So the cool thing about looking at very long wavelengths like SPT does or like ALMA does is that if we go into the infrared, we actually can see the light from that dust itself. So now we're not looking behind the dust, but we're seeing the dust itself. And so the way that I like to think about this is that there's these night vision goggles that use infrared light. And so in this case, what we're seeing is stuff that's warm. So like if you look at this person, the parts where he's bright are the legs and the arms and the face. That's because the person's skin is warmer than the rest of the stuff. And so what happens when these young stars back behind all this dust, they give off that light, the dust absorbs that light, and the dust warms up. And so it's then that warm dust that we're able to see with a telescope like ALMA. I also mentioned gravitational lensing. So this is something that I do a lot, and it's kind of complicated. But like I say, the gist of it is that basically you have a galaxy that's directly behind another galaxy between you. And so the sort of nice thing for us is that these galaxies that are in the foreground have very, very little dust in them. So if we look with a telescope like SPT or a telescope like ALMA, we only see the background galaxy that has a lot of dust. On the other hand, if we look at a short wavelength, like in the ultraviolet or something like that, we don't see the background galaxy at all. We only see the foreground galaxy. And so that is nice for our life because that means that we can see only one galaxy at a time, which is a lot easier than having to figure out what light is coming from the background and what light is coming from the foreground at any given time. And so here at the bottom is just a gallery of what these galaxies look like in general. And so you see there's kind of a wide variety of how these look. I showed one that was almost a perfect ring. Here's another one where there's like 3 different blobs down there. And all the variation that comes with this one is a smiley face. Actually, if you zoom in a little closer, one of the eyes has like a tear coming out of it, which I thought was like very emblematic of my grad school career. It's like this, happy face and a tear. Yeah, anyway. But basically, all of this has to do with just how exactly and where in relation to each other the background and the foreground line up with each other. So the closer you get to being exactly lined up, the closer to a full ring that you get. And so the cool thing about these galaxies is that they're forming stars hundreds or thousands of times faster than our own Milky Way is. So these are galaxies that are very much actively growing. And so what always tends to happen in nature, it's not necessarily obvious why this should be, but any galaxy that's forming stars 1,000 times faster than the Milky Way has tons and tons of dust in it. So there really aren't any galaxies that have a lot of ultraviolet light that are forming stars so quickly. And so if we really want to understand what's happening to these galaxies, we have no choice but to go to these very long wavelengths. And so the thing that I'm most interested in right now is how we actually get those stars to stop forming. It's kind of fun to have stars forming for a while, but if you keep letting that happen, you end up with galaxies today that are way, way, way more massive than any galaxy we've ever observed. So we know that there has to be something that keeps those stars from forming like this forever, and that's the kind of thing that I'm really interested in right now. So I will show some real images of what that looks like, but first I'm going to show a computer simulation because this is way prettier. So this is showing a computer simulation of what happens when a galaxy forms stars. On the left, this is basically just an image of the gas in a galaxy, and on the right, this is the temperature. So purple is cold, and yellowish orange is hot. And so, here, I'll start this over actually. And so what happens is that at the start of this, we're going to start sticking some new stars in the center of this galaxy. And as those stars evolve and die, a few of them will explode as supernovae. And when those stars explode, they tend to blow out tons and tons of gas from this galaxy. And so you can see that a lot of that gas is cold. It's this purple color. And then at the end, all that we're left with in the center is sort of this remains of the central disk, and then the center is pretty warm. And so this seems like a really good way to actually get a galaxy to stop forming stars, because stars form out of gas. And so it seems like all we have to do is take this gas that's in a galaxy and remove it. If we can just get it out somehow, then we can stop a galaxy from forming stars. So most of this gas that ends up out here, it takes it a very, very long time for it to sort of circulate back down and fall. And so you can effectively keep a galaxy from forming stars almost forever by doing this. This is a really pretty simulation. For those of you who do computing, this was a simulation done on GPUs or video games for that matter. So the kind of neat thing about this is that you have to do the same calculation, the same math, billions and billions of times, and that's exactly the same thing that like video games have to do. You have to render each single pixel many, many, many times. And so we can very much easily, well not easily, but you can adapt that architecture, that hardware, to do some really cool astronomy problems. Okay, so this is a computer simulation. The real thing does not look nearly as pretty because we can't, do quite so well as our friends on computers. But on the other hand, our galaxies are real, so that's kind of nice too. So here's what the actual galaxy looks like here. So now we're much more into the regime of looking at blobs. So on the left-hand side, this is basically a picture from ALMA that I've done some fancy processing on, showing a map of where the stars are currently forming in this galaxy. And on the right, this is showing an image of what we think the wind looks like, that outflowing gas from this galaxy. And so in this case, all that we can sort of say is that there's it's at least a couple blobs, and they're probably a few hundred light years across. So this may look unimpressive to you, but I guarantee you this is far better than anything anybody has ever been able to do before. And so that's kind of fun. This particular galaxy it lived at a time when the universe was only 1 billion years old. And so with this very powerful facility called ALMA that we built, we're able to do these fantastic new science products. Okay, so that's enough for me. So I'll leave you with this picture of me at ALMA. So thanks.
All right, thank you, Dr. Spilker. Okay, first question is from Twitter, and Madison at Ginger Complex has been killing it all night. Thank you, Madison, wherever you are. Where do we buy the Nibiru t-shirts?
So you can still buy the Nibiru t-shirts. I think if you just Google SPT t-shirts, the person who makes them is really cool. We have one for every year, so this was the one from 2012. And so some of them are cooler than others, in my personal opinion, and this is one of my favorites. So yeah, the person will still just screen print them on order, basically.
I cannot believe that had an actual answer.
Yeah.
Way to go, Madison. All right, questions? All right, in the back.
Yeah, so that is a very complicated question. Yeah, so the question is, why are the telescopes at ALMA not evenly spaced? And the answer is basically like, okay, so if you were to take two telescopes and put them close to each other, what we do, we don't actually take a picture of the sky with those telescopes. What we do is we take the light from one telescope and we smash it into the light from the other telescope, and we make that light interfere with itself. And so effectively what that means is that if you put the two telescopes close together, you're sensitive to very broad features in the sky. So things like very diffuse emission and that kind of thing. On the other hand, if you take your telescopes and put them really far apart, you can't see that diffuse stuff anymore, but instead you get really fine detail on small areas. And so actually they can pick up and move these antennas, these dishes, and there's like 50 of them, so they're basically like constantly moving, one or two antennas at a time. And so they sort of cycle inwards and outwards. And so they will sometimes put some telescopes really far away. They can get up to like 10 miles apart. And then sometimes they'll put them all really close to each other within like a few hundred feet.
Great question. Okay, in the center.
The question is, do we have to deal with radio pollution? And the nice thing is that actually for this, we don't really. So for these kinds of telescopes, we're looking at high enough frequencies that there's really not a whole heck of a lot of interference anymore. So if you ever like go visit the Very Large Array in New Mexico, they have to worry about that a lot more because they look at much lower frequencies where you have to worry about, satellite TV and radio and all that kind of stuff.
Okay, let's thank Dr. Spilker one more time.